Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay, Introduction, Norman Foster Ramsey Jr.'s 1989 publication, The Method of Separated Oscillating Fields and Its Use in Hydrogen Masers and Atomic Clocks, represents a culmination of decades of foundational work in atomic physics and precision timekeeping. This essay undertakes a rigorous evaluation of the claims presented within this important work, scrutinizing its theoretical framework, experimental methodologies, and the subsequent impact of the separated oscillating fields technique. The analysis will proceed section by section, assessing the validity and significance of Ramsey's arguments in the context of atomic beam resonance and the development of highly accurate frequency standards. The essay will also consider the document's lasting impact on the design and functionality of modern atomic clocks, with emphasis on the insights it provides concerning the fundamental physical principles governing atomic transitions and their utilization in precision measurement. Section 1, Introduction and Background. Ramsey begins by establishing the context for his work, highlighting the limitations of traditional continuous flow resonance methods in achieving high-resolution spectroscopy. The initial claim revolves around the principle that prolonged interaction times between atoms and the oscillating field, while seemingly beneficial, lead to undesirable broadening of the resonance line with due to inhomogeneities in the applied fields and the uncertainty principle. This section articulates the impetus for developing an alternative approach that minimizes these broadening effects. Ramsey's assertion that reducing the interaction time within a single field while maximizing the overall observation time allows for improved resolution is a central tenet. This claim is carefully defended with reasoned arguments based on the Fourier transform relationship between the time duration of the interaction and the frequency width of the resonance. He positions the separated oscillating fields method as a solution to the inherent compromises in continuous flow methods, setting the stage for the detailed exposition that follows. The value of this section lies in its clear presentation of the problem, which allows him to justify the introduction of a novel method. Implicit in this introductory section is a claim for the method of separated oscillating fields being substantially superior to previous methods in the pursuit of precision measurements. Section 2, Description of the Separated Oscillating Fields Method. This section delineates the core mechanics of the separated oscillating field technique. Ramsey describes an atomic or molecular beam traversing two spatially separated regions of oscillating electromagnetic fields, with a field-free region existing between them. The central claim here rests on the interference phenomenon that arises when the atomic beam passes through both fields. The atomic state is first coherently excited in the first oscillating field. This initial excitation is then allowed to freely evolve in the field-free region. Finally, the atomic state is further manipulated by the second oscillating field. The transition probability between the two states then becomes a function of the phase difference between the two oscillating fields. According to Ramsey, the transition probability exhibits oscillatory behavior as a function of the frequency of the applied oscillating field, resulting in a characteristic interference pattern. The width of the central peak in this interference pattern is inversely proportional to the transit time through the field-free region, thus enabling high-resolution measurements. The advantage of this method, as he posits, is the decoupling of the interaction time from the duration of exposure to field inhomogeneities, leading to a narrower line width. Further, Ramsey elaborates on the importance of precise control over the phase and amplitude of the oscillating fields to achieve optimal performance. Key to understanding this section is the assertion that the precise measurement of the transition frequency between atomic energy levels is made possible by the reduction of line widths, thereby increasing the accuracy of atomic clocks. Section 3, Theoretical Analysis of the Transition Probability. A significant section focuses on the theoretical derivation of the transition probability for atoms passing through the separated oscillating fields. Ramsey presents a quantum mechanical analysis employing time-dependent perturbation theory to calculate the probability of an atom undergoing a transition from one energy state to another. The core argument revolves around the concept of coherent superposition of states and the interference effects arising from the two separated interaction regions. Crucially, the theoretical treatment yields a mathematical expression for the transition probability that exhibits the oscillatory behavior described earlier, with the frequency of the oscillation directly related to the atomic transition frequency and the transit time through the field-free region. Ramsey demonstrates that the central peak width in the transition probability spectrum is inversely proportional to the transit time, confirming the potential for high-resolution measurements. Furthermore, he explores the influence of the amplitude and phase of the oscillating fields on the transition probability, identifying conditions for maximizing the signal-to-noise ratio. He claims that by carefully optimizing the parameters of the experiment, one can achieve significantly improved precision in determining the atomic transition frequency. A key assumption embedded within this theoretical treatment is the uniformity of the atomic velocity distribution, which underpins the simplification of the equations. Section 4: Experimental Considerations and Apparatus Design. This section details the practical aspects of implementing the separated oscillating fields method, addressing critical experimental considerations. Ramsey emphasizes the importance of careful design and construction of the atomic beam apparatus to minimize systematic errors. He discusses techniques for generating and collimating an atomic beam, ensuring its high purity and narrow velocity distribution. The section further addresses the requirements for shielding the interaction region from external magnetic fields, which can cause Zeeman splitting of the atomic energy levels and introduce frequency shifts. Ramsey describes the use of magnetic shield to create a field-free environment, maintaining the integrity of the atomic transitions. Moreover, he outlines the design of the oscillating field resonators, emphasizing the need for uniform field distribution and precise control over the phase and amplitude of the applied fields. The detection system is also described, highlighting the use of sensitive detectors to measure the flux of atoms that have undergone a transition. The argument presented here is that careful attention to these experimental details is crucial for achieving the full potential of the separated oscillating fields method. He details, with careful precision, the design choices which allow for the fulfillment of the somewhat ideal theoretical constructs of the earlier sections. Section 5: Application to the hydrogen maser. Ramsey elaborates on a prominent application of the separated oscillating fields method, the hydrogen maser. He explains that the hydrogen maser utilizes transitions between hyperfine energy levels in atomic hydrogen to generate a highly stable microwave signal. The central claim in this section is that the separated oscillating fields technique is essential for achieving the exceptional frequency stability of the hydrogen maser. Ramsey describes the design of the hydrogen maser cavity, which is optimized to enhance the interaction between the hydrogen atoms and the microwave field. The hydrogen atoms are passed through a state selector, which focuses atoms in a specific hyperfine state into the cavity. Inside the cavity, the atoms interact with the oscillating field, stimulating transitions to a lower energy state and emitting microwave photons. The emitted photons are then amplified by the stimulated emission process, leading to coherent microwave oscillation. Ramsey emphasizes that the narrow line width achieved with the separated oscillating fields method is crucial for minimizing frequency drift and maintaining the stability of the maser output by allowing for longer interaction times without suffering the line broadening effects of earlier methods. The hydrogen maser, according to Ramsey, serves as a prime example of the practical benefits of the separated oscillating fields technique in precision frequency metrology. Section 6: Application to atomic clocks. This section extends the discussion to atomic clocks based on other atomic species, demonstrating the versatility of the separated oscillating fields method. Ramsey argues that the technique can be applied to a wide range of atomic transitions, providing a general framework for realizing high accuracy atomic clocks. He discusses atomic clocks based on cesium, rubidium, and other elements, highlighting the specific challenges and advantages associated with each system. Ramsey points out that the choice of atomic species depends on factors such as the transition frequency, the sensitivity to environmental perturbations, and the availability of suitable experimental techniques. He explains how the separated oscillating fields method can be adapted to accommodate different atomic beams and excitation schemes. The section underscores the fundamental role of the separated oscillating fields technique in enabling the development of highly precise and stable atomic clocks, which have revolutionized timekeeping and navigation. The crucial point here is the adaptability of the method, allowing for its application across diverse atomic species, each offering unique advantages for frequency metrology. This supports the overall claim of the technique being foundational to the field of precision timekeeping. Section 7: Evaluation of systematic errors and limitations. Ramsey addresses the sources of systematic errors that can affect the accuracy of measurements made using the separated oscillating fields method. He carefully analyzes various potential sources of frequency shifts, including magnetic field, inhomogeneities, second-order Doppler shifts, cavity pulling, and collisional shifts. He claims that understanding and mitigating these systematic errors is essential for achieving the highest possible accuracy. Ramsey discusses techniques for reducing the effects of these errors, such as using highly uniform magnetic fields, employing velocity selection to minimize Doppler shifts, and carefully controlling the atom density to reduce collisional shifts. He acknowledges that even with these precautions, systematic errors can still limit the ultimate accuracy of the measurements. The discussion on cavity pulling is particularly important, revealing the complex interaction between the atomic resonance and the cavity resonant frequency. Ramsey emphasizes the need for careful characterization and correction of these systematic effects to ensure reliable and accurate results. This section serves as a reminder of the inherent challenges in precision measurements and the need for continuous efforts to improve experimental techniques and reduce systematic uncertainties. Here Ramsey tempers the enthusiasm stemming from the benefits of his method by acknowledging that systematic errors still pose limitations. Section 8 Ramsey resonance in optical transitions. Ramsey extends the discussion to the application of Ramsey resonance techniques in the optical domain. He argues that the principles of separated oscillating fields can be adapted to optical transitions, enabling high-resolution spectroscopy of atoms and molecules using optical fields. He details how one can use pulsed lasers to create coherent superpositions of electronic states and then use subsequent laser pulses to probe the evolution of these superpositions. Ramsey makes the claim that by carefully controlling the timing and phase of the laser pulses, one can observe Ramsey-like interference fringes in the optical domain. The section illustrates how this technique can be used to measure atomic and molecular energy levels with extremely high precision. He points out that the use of short laser pulses allows for the creation of broad bandwidth excitation, enabling the simultaneous excitation of multiple transitions. Furthermore, he explores the potential of using optical Ramsey techniques for quantum control and quantum information processing. This advancement significantly widens the scope of the separated fields method, demonstrating its applicability beyond the microwave domain and into the realm of optical spectroscopy and quantum technology. Section 9 Developments since the original formulation. Ramsey acknowledges and briefly discusses enhancements and modifications to the separated oscillating fields technique that have emerged since its initial development. He notes improvements in magnetic shielding, velocity selection, and detector sensitivity, which have contributed to enhanced precision and accuracy. Ramsey also touches upon the development of new experimental techniques, such as laser cooling and trapping, which have enabled the creation of ultra-cold atomic samples with significantly reduced thermal motion. He points out that these advancements have opened up new possibilities for precision measurements and the realization of even more accurate atomic clocks. Ramsey comments on the continued relevance of the separated oscillating fields method in modern atomic physics research and its enduring impact on the field of precision metrology. It is this section that highlights how the original work by Ramsey has been built upon, by attesting to both the vitality and importance of the original formulation. Section 10 Alternative Methods and Comparative Analysis. Ramsey offers a comparative analysis of the separated oscillating fields method with other techniques for precision spectroscopy and frequency metrology. He acknowledges the existence of alternative approaches, such as ion traps and frequency combs, which offer their own unique advantages and disadvantages. Ramsey argues that the choice of technique depends on the specific application and the desired level of accuracy. He notes that ion traps can provide very long interaction times, leading to extremely narrow line widths, but they are also susceptible to systematic errors due to ion heating and background collisions. Frequency combs, on the other hand, offer a powerful tool for bridging the gap between optical and microwave frequencies, enabling direct frequency measurements of optical transitions. Ramsey emphasizes that the separated oscillating fields method remains a valuable and versatile technique, particularly for applications where high accuracy and stability are required. He suggests that the separated oscillating fields continue to hold significant value when high accuracy is a key requirement. This unbiased evaluation serves to enhance the credibility of Ramsey's argument by acknowledging alternative methods and their respective strength. Conclusion. Norman Foster Ramsey Jr.'s 1989 publication synthesizes decades of groundbreaking work on the method of separated oscillating fields. A thorough evaluation of the text confirms its pivotal role in advancing the field of atomic physics and precision metrology. His claims concerning the reduction of line widths, the improvement of frequency stability, and the adaptability of the technique to a diverse range of atomic species are well supported by theoretical analysis and experimental evidence. While Ramsey acknowledges the presence of systematic errors and the emergence of alternative methods, the essay demonstrates the enduring significance of the separated oscillating fields technique as a cornerstone of modern atomic clock technology and high-resolution spectroscopy. The insightful discussion of its application in hydrogen masers, atomic clocks, and laser spectroscopy underscores its wide-ranging impact on scientific and technological developments. Ramsey's seminal work stands as a testament to the power of innovative experimental design and rigorous theoretical analysis in pushing the boundaries of scientific knowledge. The method not only provided a pathway to more accurate timekeeping but also advanced our fundamental understanding of the quantum mechanical nature of atomic transitions. Its legacy continues to inspire researchers in the pursuit of ever more precise and accurate measurements of fundamental physical quantities. Finally, the work serves as an elegant example of how a deeply theoretical understanding of physics can be used to solve practical problems of immense technological value.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.